So hello dear students. So today I'm going to discuss nuclear detection and how nuclear radiation is detected, and in particular I'm going to discuss what are known as Geiger Muller counters, which are the detectors generally used for simple nuclear radiation detection. So the fundamental principle behind any gas detector you can think of is basically ionization. So you have a chamber filled with gas and some ionizing radiation, either beta particles or alpha particles, they enter that chamber in which gas is filled, and it knocks down the electrons of the atom inside the gas, creating an electron ion pair, that is a free electron and a positive ion. Now gas is normally an insulator, but the radiation which produces ions inside that gas and electrons as well, it makes that gas conducting temporarily. And then what happens is, you have in that chamber you have an anode and a cathode, as is shown in this figure here. So you have a cathode here and an anode here, and this is the gas that is filling, and the ionization radiation is entering this chamber from this side. So when it enters, it strikes the gas atoms and produces an electron ion pair. So the electron moves towards the anode and the ion moves towards the cathode. And then when it reaches the anode, the electron produces a small electric signal, and that electric signal is basically measured by some ammeter or some other simple current detector that you can think of. And in that case, that small impulse or the pulse that is generated, the current pulse, acts as a signal for the presence of the nuclear radiation. So when we talk about the basic detector anatomy, it basically consists of a sealed chamber. So here we show a cross section of a simple gas detector. So it is made up of a sealed chamber, and in that sealed chamber you have two electrodes. One of them is the anode, which is in the form of a thin central wire, and then you have a cathode, which is a cylindrical tube which is encircling this anode. A high voltage supply creates an electric field inside. So the voltage it is supplied, and that voltage basically between the anode and the cathode produces an electric field. And the geometry of the electric field is cylindrical. So basically near the anode, the electric field is of very high intensity, whereas as it moves out ahead apart towards the cathode, the intensity of the electric field decreases. So basically it's near the anode, where the electrons are generally accelerated to a very high degree, and they produce a very high amplification because of that. So here we show a characteristic curve for the gas filled chambers. So the behavior of the detector depends upon the voltage that is applied to the detector. So there are several distinct phases or distinct regions you can talk about in which the gas filled detector operates. So basically in the initial region, if we on the x-axis you are plotting the voltage that is applied, and on the y-axis you are plotting the pulse height, or you can say the number of signals that are collected. Then in the first phase or the first region, the pulse height increases slowly, and basically it is used when only one electron or one single uh, electron has to be detected, or one single radiation particle has to be detected, but it is not able to produce a very high or very high amplified signal, so it is difficult to detect in this range. And then in the ion chamber region, that is the second region that we are talking about, we are showing two different lines, the red line and the blue line. So the blue line is basically is for the radiation which is having a higher energy, and the red line is for the radiation which is having lower energy. And so you can see in this ion chamber region, as the energy increases, the pulse or the signal amplitude also increases proportionally. So that is the basic principle behind proportional counters. That is, the single signal is dependent upon the energy of the incoming radiation. It is proportional to the energy of the incoming radiation. Then in the proportional counting region, as you increase the voltage, so the signal pulse is proportional to the incoming energy, but it is also proportional to the applied voltage. So it increases linearly with the applied voltage in the two cases, one with a higher energy and the other with a lower energy. And then again there is a next region in which the two basically the two different curves, they meet, and this is the region which is not used when we are talking about operation of a gas field detector. And finally you have a Geiger region in which you have so much of radiation which is penetrating and producing so much of ions throughout the chamber that the signal that is produced does not depend upon the energy or the voltage. So it remains constant throughout this region, and you have a generic kind of a signal that is produced, and that signal is basically independent of the applied voltage or the incoming radiation. So this region is called the Geiger region. And then also you have another region in which the signal increases exponentially. So that's the breakdown region, and that breakdown region is again not used when you are talking about radiation detection. So here we have described the three regions. The number one is the ionization radiation or the ionization region, which is operated on low voltage and collects only primary ions created by the radiation. So single electron is collected by the cathode and the anode. So as such, though amplification of the gas takes place, so no secondary electrons are generated, and it is used for accurate dose measurement. That is, basically generally it is used when we are talking about number of particles that are entering, what are the number of particles that are entering a region, so that for that accurate dose measurement this region is used. Then you have the proportional region, which is there in the intermediate voltage range, and in that case what happens is electron gains energy to create secondary ionization, and that is called as Townsend avalanche. So I will discuss Townsend avalanche later on in this particular uh, video itself. And because of that secondary ionization, amplification of the signal takes place because large number of electrons are generated and they reach the anode and produce a large signal. So a controlled gas amplification of the order of 10 raised to power 3 to 10 raised to power 5 is produced in the proportional region. And the output pulse is proportional to the incident initial radiation. So whatever is the initial radiation, the output pulse is proportional to that. And it is used for energy spectroscopy, basically to find out what is the energy of the radiation. Then finally you have the Geiger-Muller region in which a very high voltage is applied. So in that case, the ionization that is produced by the incoming radiation, it triggers a massive saturated avalanche along the entire anode. So a large number of electrons are produced as secondary electrons. So they generally, the number of electrons that are produced, that they just don't depend upon the original energy of the radiation. So whatever is the original energy of the radiation, since the secondary production of secondary electrons is so large, so it becomes uh, totally saturated with energy and radiation, and that results in huge amplification of the order of 10 raised to power 8 to 10 raised to power 10. And the outpulse is large and independent of the initial energy, and it is used simply to detect the presence of radiation in the medium or the surrounding area or the region. So basically it is for simple sensitive detection of radiation. Whatever radiation is present in a given region, it is used for that, and generally this is the basic principle for GM counters. So this is the picture for a GM counter. Here you have a tube or the gas chamber, and here is the connected ammeter or the voltage pulse meter, which is measuring the pulse that is generated by the incoming radiation. And this at this end you have the window through which the energy or the radiation is entering. So this is the dissectional view of the Geiger Muller counter. So you have this window here, and then the ionization radiation is entering this window, and that is producing ionization inside the chamber, and you have an anode and a cathode which is connected to a meter, and then the pulse is basically measured by this meter, which is produced when the avalanche action takes place and a large huge number of secondary radiation is produced, and because of that a huge current of the order of let us say the voltage of the order of 1 volt is produced. So no further amplification is also required for the signal, because a large voltage is produced, and that can be measured here with this particular meter. And also you can hear the sound of the clicking sound of the pulse. So the clicking sound, if there are number of radiation particles are entering, so first particle will produce a click and the second will produce another click. So different clicking sounds are generally produced whenever you are using a GM counter, and that you can hear, that clicking sound you can actually hear, and that actually is the basically the result of the ionization that is produced by the incoming radiation inside the gas chamber. So basically you have, as I told you, the geometry is the anode cathode geometry, a thin central wire which is an anode and a cylindrical cathode. But there are different types of GM tubes constructions. One type is called the end window construction, which is basically I've shown in the earlier slide. So you have a thin mica window for weakly penetrating particles like alpha and beta particles. Then you have a pancake type of geometry in which a large flat window, it is used for surface contamination surveys. Then of course you have a windowless, that is a windowless detector in which there is no window, so there is basically an opaque cylinder, and the more penetrating radiations like gamma rays, which can penetrate a thick wall of the cathode, they are produced and they are used for detection in this windowless type of GM tubes. And inside, the gas is basically made up of 90% inert gas like argon or neon, and 10% of quench gas, which is either halogen or organic. So we will discuss the role of these two gases later on in this slide. So here what is shown is the Townsend avalanche. So basically it's a Geiger discharge, or what is happening, a chain reaction is taking place. So originally one event takes place, or an ion electron is produced, and when it moves forward it produces further other secondary ion electrons, and so it triggers a chain reaction, and gradually a large number of ions are produced in a form of an avalanche, and it spreads throughout the tube. So basically it is not just confined to one single region of the tube, but it starts spreading throughout the tube. And during the propagation, what happens is when the uh, electrons are generated, they strike other atoms, they produce UV photons. So those ultraviolet photons, they travel very fast throughout the tube, and within the time period of microseconds, The whole of the tube is filled with ionization or ions and electrons, and so and the whole tube is filled with ionic particles, and so as a result a massive cascading discharge spreads through the entire anode in microseconds. Now what happens is when the ions, they reach the cathode, the electrons reach the anode and they produce a pulse, but ions are which are positively charged, they reach the anode, and when they reach the anode, what happens is when they strike the anode, the energy may be sufficient to produce some extra electrons which can trigger another avalanche. So this process will not stop at all, because whenever on the anode, if the ions are reaching and they are producing secondary electrons, they will again enter the chamber and produce another avalanche, and this process will continue indefinitely. So to stop this, a quench gas is used. So basically the quench gas is basically a high molecular organic gas or halogens, and what happens in that case is when the ions are traveling through the gas filled chamber, and in that case they strike those quench gas. So the quench gas has a complicated molecular structure. So basically what they do is they absorb the energy of the uh, ions, and they get ionized in the process, and those ionized quench gas, when they strike the cathode, the energy that is required to release the electron is now absorbed by this quench gas, and the dissociation of this quench gas is taking place. So either halogen or like bromine or chlorine is there. So the energy which would be required to produce an electron would actually be absorbed by these gases, and they will break down into their atomic constituents. And in the case of halogens, these atomic constituents recombine and again form the gas, either chlorine or bromine. So in that case, the tube, the Geiger Muller tube, has got a long lifetime. Whereas in case of organic molecules, they break down and they do not recombine. So you have to replenish the tube again and again after a certain number of uses have taken place. So another thing that happens in the GM counter is the dead time. So what happens is massive discharge creates a cloud of positive ions around the anode. So the anode is covered by the positive ions because they are slow to move. So they are not moving that fast compared to the electrons. So they are not reaching the cathode that much of fast compared to the electrons, which are basically moving very fast, and they reach the anode very fast. So they create a kind of a, what you can say, a cloud, which temporarily lowers the electric field inside the detector. And once that cloud is formed and the electric field becomes low, what happens is that detector becomes insensitive to the radiation, because the electric field has become low during that time. So a new radiation that would come will not be accelerating and will not produce electrons which will accelerate and produce a discharge. So a certain amount of time is required, which is typically 50 to 200 microseconds, in which time the detector cannot register a new event. So that is called the dead time of the detector. So during that time, the detector becomes insensitive or inactive, and once that cloud is again it vanishes, or it disappears, and again at that point of time when the required amount of time has passed, again the detector becomes active, and in that case what happens is something like 50 to 200 microseconds is required for the detector to register a new event. So what are the strengths and weaknesses of the GM counter? Strength is it is very sensitive because of the huge amplification. So the amplification is so large that it is becoming sensitive. So it's producing a very high voltage. And so even a small ionization can produce a very large amplification. So that makes it very sensitive. And it is simple and low cost The large output pulse requires simple, inexpensive electronics. So because the output pulse is very large, so the electronic which is required to detect those pulses is not that complicated or costly. And so inexpensive electronics can work there and can be beneficial to give you the proper output reading. It is robust and portable, so it is good for field investigations wherever you are working in the field and trying to detect radiation. It is not sensitive to minor fluctuation of voltages, but the weaknesses are also there. The weakness is that all pulses are of the same size. In the Geiger-Muller region, you have a very high avalanche kind of a situation in which the signal becomes extremely amplified and it is not proportional to the incoming radiation energy at all. So it remains constant and it is unique signal that is produced during that particular region when the counter is operative in that particular region. So you cannot identify the energy of the incoming radiation, and so at the same time you cannot also, because of the dead time, for a certain time period the instrument becomes inactive, and so in that case again it is difficult during that time to measure any radiation, and it has got low gamma ray efficiency. It is not very good for gamma ray detection. So application of GM counters is it is in the health physics, contamination survey, in area radiation monitoring, personal frisking, emergency response, like for rapid hazard assessment by the responders. There are in some chemical or physical hazard has taken place due to radioactivity, and in that case a rapid measurement is possible. And in industrial and research, so a routine monitoring, geology, educational experiments, etc., it is used. So in conclusion, gas field detectors are unified by the characteristic curve when applied, where applied voltage dictates behavior. So basically it's the applied voltage that dictates what behavior the detector is going to have. So basically the output of the detector depends upon the applied voltage. So that is called the proportional characteristic of those gas field detectors. And then in that case, Geiger-Muller counter maximizes amplification to achieve incredible sensitivity, and it is achieved by Geiger discharge, which is a self-propagating avalanche. Quenching and dead time are the defining operational characteristics, and despite its limitation, no energy information and long dead time, the GM counter sensitivity, simplicity, and low cost makes it an indispensable tool for radiation protection and detection.